Hello, young astronomers. Today we're going to talk about telescopes. Let's review the telescopes we've already talked about. Galileo and his telescope revolutionized the science of astronomy. Herschel's telescope, where he discovered Uranus, and um, we studied the orbit of Uranus and were able to discover another planet called Neptune. Um, the Hubble Space Telescope, the pictures of the galaxies, the pictures of the planets I will show you, probably 80% of all of the images I will show you in this course were taken by this Hubble Space Telescope. It's an actual telescope that is in outer space. We'll learn why it's in outer space today, not to get it any closer to the objects. It's in the orbit around the Earth. It's not. That's not why it's in space. And we briefly mentioned this telescope. This is actually Edwin Hubble, the person that the Hubble Space Telescope is named after, and that's a telescope that he discovered that Andromeda wasn't just a smudge of light, was an actual other galaxy. Let's also review what we learned about light in the first lecture this week. If you haven't watched that lecture, it's probably better to watch it first. We learned that just by analyzing the light coming from an object, we don't just take images of it. Images are spectacular and beautiful, and they move us, but we break that light up through a spectrograph. We break it up into its different energy levels. Remember, every color of the rainbow is a different energy light. And visible light is only a small portion of the entire electromagnetic spectrum that ranges from the lowest energy to radio waves, to microwaves, to infrared light, the Navy SEALs light, the visible light, ultraviolet light, X-rays, and gamma rays. All of those things are the same thing. They are particles of light called photons that have zero mass, or we can also think of them, it's not just thinking of them, they exhibit wave properties. And we talked all about the different wave properties, the relationship between the wavelength and the frequency, and the relationship between the energy of a photon and its frequency, or the energy of that wave and its frequency. But by breaking that light apart into its different energy levels, there's many things we can learn about an astronomical object, whether it's a star or a galaxy or a planet, or even the cold gas, or in outer space before it even makes anything. We can learn its temperature. We can learn its chemical composition. Remember, there will be absorption lines in the light from that star. And each one of those little dark areas corresponds to a different element, a different molecule. So we can tell what the chemical composition of an object is. We can also tell how fast it's moving, and whether it's moving closer to us or further, or faster towards us, or away from us, by measuring how those lines switch. The spectral lines will, we call it redshift. If the object's moving away, they'll get shifted to lower energies, higher wavelengths, the redder part of the visible spectrum anyway. It's not that the object's going to really appear redder, but it'll be a subtle shift in the absorption spectrum. So we can't do that kind of stuff with our eyes. We need a scientific instrument, and that is what we're going to talk about now. Those are the telescopes. Here's just a really quick review of everything we talked about. Try to keep up. No, let's get to. And we did a lot of work already this week, didn't we? Okay, so, but the eye, speaking of our own eyes, it actually is, it was really the first telescope. It has a lens in it. Remember, we learned that light gets bent when it travels through a different material than air. And so our eyes, even without glasses, have lenses in them, and it actually bends the light, which is good because the light detector, if you will, the cells on the back of our retina that actually detect this light, they're very tiny. And so we have to get that light bent. We want to look at a mountain. We want to look at something far away or even something close up. Without those lenses, everything, we would just have we would just see a tiny little dot of light coming through there. So we need that light to get bent so it can actually, a large object turns into a smaller one. And so the lens in our eye actually does that. A fun fact is that if you just have one lens in your telescope or your eye, the image gets inverted. If you trace the light coming from the top of the object, it gets bent. It ends up in the bottom part of of the back of our retina. If the bottom part ends up top, the image is actually inverted. Our brain has to interpret that as a right side up image. And even the early telescopes only had, Galileo saw everything upside down. His telescope only had one lens in it. So how do we characterize telescopes? A telescope is basically a giant bucket to collect light. Instead of collecting water, we want to collect photons. You can imagine, look, the opening in your eye, the pupil is very tiny. Imagine you're out in a rainstorm with a little thimble trying to collect water. You want a bigger bucket. You want a big Home Depot bucket, or you want a big rain barrel. The bigger the bucket is, the more light you can collect. Scientifically, we call that the aperture. It's really the diameter of the opening of the telescope is actually the most important characteristic of a telescope. That allows us to collect more light. If you get a big enough bucket like that, let's say it's misting out, you can collect a lot of light. You can actually see stars during the daytime. If you point a telescope away from the sun, you can actually see the stars through there. If you point it in the direction of the sun, it's still going to blind you, but it can see better than our eyes. We can actually see stars during the daytime. We still wait at night to really see them. Another thing is we can adjust the exposure time of a telescope, whether we're taking a photographic image of it or we're recording it digitally. We can leave that bucket, the lid off that bucket for a long time. Our eyes actually refresh the image thousands of times a second, which is great when you're running from a Jaguar and you need to know where it is at every second so you can make a fast move. But if you're trying to look at something very far away, it's not very good. A telescope, we can actually adjust that. So many of the images you see that we publish are better than what you would actually see looking through a telescope because your eye, even when you look through a telescope, your eye is refreshing that image. You don't get the full effect. But we can record it digitally, which you can look at later, and we can collect a lot more light that way. But another important characteristic is the resolution. We want to be able to distinguish objects. It's not just about collecting a bunch of light. We don't want it to look like a big blob. So the other characteristic is resolution. We want to be able to distinguish objects that are very close together or small features on the moon, for instance. We want to be able to look into the craters of the moon. We want to look in the sky, and many of the stars we see with our eyes are actually double stars. They're called binary stars. Some of them are even 3 stars that orbit each other. We'll learn about that actually next week, how stars are formed. Very often they form in pairs or even triplets. Probably there's a star system that has 4 stars out there. I'll have to research that. See if we found one of those yet. I'm sure there's one. It's just a matter of us finding it. To a lesser extent, that's actually the length of the telescope gives us better resolution. So you're seeing, we want to make these things big. You noticed Galileo's was a little one, and then Herschel's got bigger, and then bigger and bigger. So we want them fat, and we want them long, and that'll give us our best images and our best scientific readings on them. Magnification is nice. It allows us, especially if we're looking with our eyes that we're trying to you know, if you're doing amateur astronomy and you just want to go have see a nice picture, it'd be nice if it got bigger. The problem with magnification is that it's usually at the expense of resolution. So you get a bigger picture, but it's more blurry. So astronomers don't really worry too much about magnification. Um, uh, so how does a telescope work? Again, remember when light goes through an object, it gets bent. We make what's called a lens. It actually gets bent as it leaves, and so we can manipulate the path length of light by putting it through these lenses. And what that does to us, that's actually what gives us the resolving power, right? The opening just allows us to collect a bunch of light, but the lens is what actually separates that light into its distinct regions. So, for instance, the easiest way to think about this is two stars that are very close to one another. In this image here, the red rays are the light from one star, the blue rays are the light from another star. And you see about an equal amount make it through our opening, so we would just kind of see one object, one kind of fuzzy object. But if we run that through a lens, we notice we can focus the objects on two different parts, and we actually get to see that they are two stars. And you'll notice that the longer I make that focal length, you don't really that in order for me to make a longer focal length, I have to make a bigger telescope. You probably know about this with cameras, right? You see if you want to take a picture a long way away, you basically have a miniature telescope. Those long, they call them telephoto lenses, are basically telescopes. It's the same thing. It allows us to see these objects that are close. You can't even tell they're the different objects with our eyes. We can actually resolve them better with the telescope. So the gist of this is, again, wider, fatter, and longer, the better the telescope is. So that is what Herschel's telescope was. You can see, trying to make these things big, the lens is on the end of this. That's why you had all that scaffolding to kind of hold up this massive lens. We actually don't use telescopes like this much anymore. Almost all professional telescopes those are called refracting telescopes. We use reflecting telescopes. Instead of lenses, we use mirrors to reflect the light. And you can see we get the same effect. Again, we have the red star, blue star, we bounce it around and we get two separate images of that. Guess who invented the reflecting telescope? Sir Isaac Newton. Understanding the laws of motion and the law of gravity and breaking apart light wasn't good enough. He actually invented the modern telescope, reflecting telescopes. Almost all professional telescopes are this way. Even most amateur telescopes are reflecting telescopes now. You can see a huge advantage of this is the guts of this, the heavy part of this is on the ground. It's not way up in the air on the other end of the telescope like it is on the refractors, right? You have to support this. With this, all you need is a kind of a hollow cylinder up here. And then the other advantage to this is you only have to have one perfect side of the mirror. A lens has to have both sides perfectly shaped and no impurities in between them. And so it's just a lot easier to make lenses or to make mirrors than it is to make lenses. It's still a huge undertaking for these giant telescopes, but it's a lot easier to make a mirror than it is to make a lens. And so most telescopes these days are reflecting. Here is a resolution at work. This is with a telescope that doesn't have good resolutions, but still better resolution than our eyes. To us, we wouldn't even see this. We would just look like a spherical blob. You can kind of see it's getting a little more oval. Might imagine that there's one part here emitting light here and another one here. But if I have a telescope that has better resolution, I can actually tell there's two different stars. Be careful with resolution. The resolution is the smallest object it can tell apart. So we actually want low numbers for resolution. It's not like TVDs or megapixels on our phones. With we want big numbers. We actually want small numbers for the resolution. They're kind of talking about the same thing, but in the case of a telescope, we talk about the smallest things we can actually resolve. So telescopes that have small resolution are the best ones. Our old friend Polaris. Remember, if you did not go out and observe Polaris, go and do it. You can go back and do that assignment, whatever. I know our observational deadlines are based on weather. So I know there was fires and smoke, but go see if you can find Polaris. And now, if you already did, go look at it again, and now realize that it's actually 3 stars. If you looked at that, even an amateur telescope, you could probably see 2 of them. If you get a professional one, you'd actually see that there are 3 stars. Polaris is actually 3 stars in orbit around each other. The next revolution in astronomy was actually photography. As I said, this allows a permanent image. The ancient astronomers had to be artists as well as scientists. They had to they draw pictures of what they were looking at in order to tell somebody about it. Other than inviting them over to look through their telescope. So we have a permanent record, and just as important, if not more important, we can adjust the exposure time. So we can allow more light. Leaving the lid off the bucket during a rainstorm, we get more light. So we can adjust that time and see things at finer detail and that are dimmer. We do not even do normal photographs anymore. Just like probably, I don't know, maybe, well, I guess some aficionados still use film for photographs. You'll have to tell me about whether whether actual moving pictures are shot on actual film versus digital. I imagine it's going towards the digital part of that. But in astronomy, we have completely switched to digital. It allows us to look at the images instantly, no development. We can send them across the country, the world, much easier. And it's the camera in your smartphone was actually developed by astronomers to make digital pictures of astronomical objects. It's exactly the same, only ours are better than yours, and they can be bigger, right? We don't need this to be portable. These things are the pixel detectors are about that big versus a tiny one on your phone, and they have they're very efficient, and so they're called CCD, charged coupled devices. And unlike your phone, which can only detect visible light, these can detect infrared, ultraviolet, all different kinds of light they can detect. So you may have noticed already that we put our telescopes out in the middle of nowhere, and we put them as high up on Earth as we can. The middle of nowhere, and both of those allow us to get rid of the light pollution, right? So again, also, if you're having trouble seeing objects in LA, go get on top of a roof. You'll get rid of all of the ambient light from the streetlights. They are pointed down, so you can get rid of a lot of the light pollution just by getting up on a building or going into the hills. You can see the stars much better. We do that professionally. We build our telescopes on mountaintops. We build them in the middle of deserts. We want to get away from as much civilization as we can, but there's also an advantage of going higher up is we reduce the atmospheric effects. We will learn that our atmosphere it's particles. It's held to the Earth by gravity, just the way we are. But the closer you are, remember Newton's law: the force of gravity is stronger the smaller the closer you are to the center of the Earth. So our atmosphere, gets thinner as it goes up because the particles that were higher in the atmosphere can escape into space because gravity is not as strong to them, so they can escape. So the thickness of our atmosphere is not constant; it gets thinner as you go up. Um, if you've ever climbed a mountain, if you've ever gone in the mountains, they call it altitude sickness because there's not as much oxygen in the air as you go up there. It's not so good for our respiratory systems. It's great for astronomy because, again, think of light as little particles coming down to our telescope. Uh, uh, it's got to make it through the air and it bounces around. And by the time this is the light from one star, by the time it bounces around a lot of atmosphere, it'll give us an image like this. If you're looking at it with your eyes, it's not a big deal because it's refreshing all the time. But if you're taking a long exposure, as we want to see distant objects, we get multiple images of that. It just looks like a blurry image of the star. So this is why the Hubble Space Telescope is in outer space because there's no atmosphere up there. We call this atmospheric blurring. So we build telescopes as high as we can. We shoot them into space to get rid of this atmospheric blurring. That's not the only reason we shoot them into space, but that's the way the Hubble is in there. It uses visible light, and so we launched it into space to get rid of this atmospheric blurring. Here's an image of a picture of Jupiter during a windy night versus a nice calm night, or a windy side of the mountain with a lot of turbulence versus the flat side of the mountain. These images were taken in Hawaii on different sides of a mountaintop. One side we have nice flat air that's been going for thousands of miles, and we get this great image of Jupiter. But when that air starts to bounce around, it's kind of looking at something in the bottom of a pool. It's hard enough anyway, but if people are splashing around, that image is going to shake around, and that's why we get this blurry image of Jupiter. But for other kinds of light, the atmosphere doesn't just blur it, it blocks it. And some of that is good for us. Some of it is bad for astronomy. There's certain radio frequencies that we can't detect that won't make it to Earth, but most of them are. That's good. We call a radio window. So the light from gases, light from almost everything emits some kind of radio waves. We can see that on Earth. We'll talk about the issues of that in a bit. That doesn't mean that radio astronomy on Earth is easy. It's actually quite difficult, and I'll explain why in a minute. Infrared light, the light from planets, doesn't harm us, but it doesn't make it through our atmosphere. So we have to send the Spitzer space satellite, the Kepler space satellite, the satellites that we want to detect exoplanets with, and also we'll learn that the very oldest galaxies, even though remember the light from the oldest galaxies is tens of billions of years old, up to 13 billion years old. As bright as it was, as the universe expands, remember that's the wavelength of the light. Even if it started as visible light, as the universe expands, it changes the wavelength. It turns it into a different kind of light. Turns out the oldest galaxies actually emit infrared light. And so Hubble won't be able to see them. We're going to put the James Webb Telescope up there that will have infrared cameras on it that will be able to see the very, very oldest galaxies of the universe. We get pretty old with Hubble, but we need an infrared telescope. The Spitzer Space Telescope has actually observed some of those older ones, but it's getting old. Visible light, most of it makes it to Earth. Remember, this is sorry, I didn't explain that. This is the opacity. This is how much light gets blocked. So if it's 100% opaque, that means none of the light gets through. So you see, there's regions of the infrared where it's basically none of it gets through. Almost all of the radio light gets through in this range, but in this range, none of it gets through. You'll see the visible light, most of it gets through. And again, the fact that the fact that these are the colors of the rainbow that we see that's not a coincidence. That's the light that our star puts out. It's also the light that makes it through our atmosphere. That's why our eyes have evolved to see that light. If we were on a different planet, our eyes may, with a different atmosphere, our eyes may have evolved to see infrared. Remember, the creatures who hunt at night do see a little bit of the infrared. But maybe, depending on the atmosphere, those aliens only see radio waves. Let's go to the higher energy part of the spectrum, the X-rays and the gamma rays, the most violent objects in the universe. Quasars, supermassive black holes, neutron stars, black holes colliding, all of the most hold on a second. I need to take a quick break and plug in my laptop. Sorry. Okay, sorry about the delay. We were talking about X-rays and gamma rays, the light that the most violent objects in the universe emit. We want to study it, but we don't want that stuff hitting us. That would be catastrophic to our bodies. Recall, I mentioned a couple days ago that a gamma ray burst. We think this one of the mass extinction events on Earth. The leading hypothesis for it is a gamma ray burst entered our atmosphere from a nearby supernova, and it did. Our atmosphere protected us from the gamma rays, but those gamma rays kind of destroyed the ozone layer. And the ultraviolet light killed almost everything on Earth. We don't want this ultraviolet and X-ray and gamma ray light hitting us, especially if we're mammals. It's very dangerous to it. It's like little bullets. It damages our cells. Can kill us. If it doesn't kill us, it'll give us cancer. But we want to detect that light. We want to study supermassive black holes. So again, we put telescopes out in space. So there are two main reasons for putting telescopes in space. One is X-rays, gamma rays, and a lot of the infrared part of the spectrum do not make it through our atmosphere, so they have to be in outer space. But we also put visible light telescopes in outer space, or at least we did. Hubble is out there. And so to get rid of this atmosphere, this blurry effect from the atmosphere. But we can do better. There's Hubble in all its glory, my favorite piece of scientific equipment. Here is the replacement for Hubble. It will. This is a funny story. Notice this says will launch in 2018. That was after I had redone this slide probably twice before that. I refused to make it again until it's up. Just to tell you, the latest date for the James Webb Space Telescope is May of 2021. And it's frustrating, but it is not unreasonable. The delays in getting this thing in the sky are not. It's just this is cutting edge technology. And this telescope, I don't know if you recall the history of Hubble, but first of all, when Hubble first went up, the mirror was not perfect, and then we had to send a space shuttle mission to correct that. But then even after that, we have upgraded Hubble 6 times, put different cameras. Hubble's been in the sky, been in orbit for 26 years now, and so as our technology has improved, we put better cameras in there. This puppy is not going to be in Earth orbit. I mean, it's going to orbit the Earth, but not in low Earth orbit, as we like to say. It is going to be in a special place where the gravitational kind of a a soft spot in the gravity, a place where the pull from the sun and the pull in the opposite direction from the Earth are about the same. So it'll be easier for it to stay in that orbit, and it'll be easier to steer with all that stuff. It's about 1,000,000 miles away. Um, and so we're not going to be able to do any repairs of this thing, or at least not easy repairs of it, with a shuttle mission. We'd have to design a new shuttle to get out there to fix this thing. So this thing has to work perfectly. And it is state-of-the-art, cutting-edge technology. And so while the delays are frustrating, it's reasonable. We have to get this right before we get it in orbit. And it also, no, this thing is gigantic. Look at that in person. You can't launch that. You can't put that in a capsule of a spaceship. It's too big. This thing kind of compacts and then it folds itself out into the giant mirror, and then it's got this giant sun shield as well. And so with all of this is compact, and then when it gets into space, it kind of extends itself out. It's a remarkable piece of machinery already. It'll be fantastic when we get it into outer space. But in the meantime, we can do a lot better from Earth. James Webb's primary mission is to look at infrared light, the light that gets blocked by our atmosphere. But we have learned how to get rid of atmospheric blaring. If you remember, I showed you this slide our first day, my first lecture to you. And I said, yes, those are really lasers. Those are lasers. What we do is we shoot 2 lasers into the sky or more, and we have them hit each other and make an artificial star in our atmosphere. And then we see how our instrument, how that star shakes around. And then we can use that to correct the images we take with a telescope. This is called adaptive optics, and we can correct for those atmospheric distortions. And I dare say that the very latest telescopes with adaptive optics take better pictures than Hubble does. Take better, or at least on the same level, images as Hubble. And there's a whole slew of these new telescopes that are coming online that are even more state of the art than the ones we have at the moment. Why is this not working? Okay. No, because I had to replug my laptop in. So here's an example of how adaptive optics works. This is a picture of Uranus from one of our best Keck telescopes in Hawaii. And it's pretty spectacular. You can see the rings. We'll learn that not just Saturn has rings. All of the outer planets have rings. We can see Uranus. We can see Triton, one of its bigger moons, its biggest moons, actually the biggest moon in the solar system. But this is so far away. It's pretty awesome that we can see that. We can actually see a little bit of the weather. We can see that there's something, some kind of weather structure in the atmosphere of Uranus. With exactly the same telescope, same cameras, everything. The only difference here is the adaptive optics correction to that. Look at we can see the fine structure of the rings of Neptune. We can see another moon that we couldn't see before. We can see we can really start to see weather patterns on here on the planet. And so our ground-based telescopes are very good now. We will not be sending a visible light telescope into space anymore. We've learned how to do it just as well from Earth. But like I said, we still have to send telescopes into space if we want to look at X-rays, if we want to look at most of the infrared, if we want to look at gamma rays. We don't just use one mirror, one prism like Newton does, but we have what's called a spectrograph, so we can break up that light from the planet or the galaxy or the star, and we can get it into its individual energies of light, different colors of light. And so we can learn a lot more about it by looking at the fine structure of the light coming from there. Remember, we're looking for little dark bands on here to tell us what the chemical composition of the star is, or whether it's moving towards us and how fast it's moving towards us or away from us. So we have radio telescopes. The X-ray, I mean, the X-ray telescopes just look like little boxes, but they don't even look like telescopes. And X-ray and gamma rays just like the little boxes because it turns out. Let's go back to our bucket analogy. Remember, the smaller the energy is, the longer the wavelength is, and radio waves have the longest wavelength. So when I'm trying to collect, this is where it really starts to exhibit those wave properties. If I'm trying to collect, I'm not trying to collect little pieces of water, drops now. I'm trying to collect. I'm trying to collect the wave. I'm trying to get all the information. I need to capture all of that wavelength. So I need my bucket to be gigantic. It's like trying to collect hail, and then it's like trying to collect I don't know, a giant swimming pool of water. So we need a bigger bucket. So there's two ways to do this. One is to build a giant bucket, and this is there's Arecibo radio telescope in Puerto Rico had the record for a long time of the largest telescope. It was built in between. This is a valley. This is not the one in Puerto Rico. This is the one the Chinese just finished building. I mean, that is, this is be a nice mountain valley in between here. And that's how big that is. Even the smallest ones are like your DirecTV satellite on steroids. But there's a limit to this. We want to see things that have even higher wavelength. This is good for some things, but we want to see everything, of course. And so we learned a better way to do this is by making what's called an array. So I use it. These are still gigantic telescopes. I mean, this is a person. This is a landing for a person here. So that's about the size of a person there. So they're already huge. But I connect these two electronically, and this looks at one part of the wave. This looks like at another part of the wave, and this looks at the other part. So I've effectively made a telescope that has an aperture the size of the desert by connecting these telescopes together. And so I can detect even longer wavelengths of light. And actually, if you all were paying attention to the news a couple of months ago, it was about 6 months ago, I guess now, we saw the first ever image of a black hole. It's black, like we expect. This image, we'll talk more about this image. This is not invisible light, even though this object emits a lot of visible light. This is actually the supermassive black hole at the center of not our galaxy, but of a galaxy very far away. That light had to go through, the visible light just has to go through too much stuff to get to us. One of the good things about radio waves is it does not interact with matter very much, right? Remember that hydrogen and gas and the elements that are in between the stars, they absorb visible light. Right, that's what we learned about. The wavelengths of atomic transitions are invisible light. So the visible light from this monster basically gets blocked out by the dust and gas. But the radio waves go right through that, and that's what we were able to detect. So this image was actually taken in the radio part of the electromagnetic spectrum. That's what it looks like. This is not an image. This is an artist's impression of a supermassive black hole. It's got a bunch of gas rotating around it. That gets hot, and that emits some radio waves. It shoots out material on its axis. But remember, the space-time is so curved that some of that light gets bent and shot towards us, and we get an image that looks like this in radio waves. We didn't didn't just use one array of desert telescopes. We used several, and we linked them together electronically. This is called the Event Horizon Collaboration. So we linked many of the major radio telescope arrays, and we had them all point at the same region of the sky at the same time, and we made an image. We basically made an effective telescope that was almost the size of the Earth, one size of the Earth. So we did that. This is what we predicted that picture would look like. It looks pretty close. It's blurred out when we get a more if we can make a bigger array. They're talking about adding more telescopes to make this. The bigger that is, the better detail we'll get. And we're talking about making these in space to make it even bigger than the Earth, to see even the things. There's another supermassive black hole. When they took this is not the picture of this previous thing that I showed you is not the picture of our supermassive black hole. That's a different galaxy, but they also took one of our supermassive black hole, and maybe by the time before this course is over, we'll actually get that. They're still analyzing the data. I will link. It's not up there yet, but I found a really cool video that explains all of the hoops they had to jump through to get all of this data collected. One of them was just collect. They couldn't. They took so much data that you can't transmit it over the internet. So they had to fly down to Antarctica to get the disks. And you can only fly in Antarctica for a certain amount of a very short window of the seasons down there. So they had to wait for summertime in Antarctica to fly down there and get the data because they couldn't transmit it over the internet. They took so much. Here's not exactly our latest. We'll talk more about our latest version. Our latest version of infrared telescope is called TESS, and that has replaced Kepler. We'll talk about that in a couple weeks. But Kepler, those exoplanets that we've discovered so far, most of them were discovered with Kepler. Kepler does infrared. Spitzer does infrared. Fermi, their openings don't have to be so big because the photons they're looking at don't have long wavelengths. You still want them big, but not. You don't have to make them as big as for a visible telescope. And for X-rays and gamma rays, you barely need a little opening to get them in there. So these telescopes have to be in outer space. And it's really interesting that we learn all sorts of different things about objects by looking at the light from them in different wavelengths. For instance, this is a thing called the Crab Nebula. It is gorgeous invisible light, but we can study it in radio waves, and that can tell us what the composition of that is, right? We can tell how much hydrogen is, how much heavy elements are in there. We can look at the ultraviolet and see kind of it turns out the really heavy metals interact with ultraviolet light. So this is kind of our this is right after supernova, so we can see that heavier elements have been formed. And then if we look at the X-ray, we actually see this weird image of something rotating around a central object with these jets coming out of that. That's actually an image of a neutron star in X-rays. We'll talk about that, but we never know that there was a neutron star here by just looking at the optical link. And actually, we saw the pulses of this in the center here in the radio spectrum. These neutron stars are like lighthouses, and when they're shooting out material, when that material is in our direction, we get a radio signal. And so we learned a lot about this by looking at the different kind of light. Here's Andromeda with visible light. Here is Andromeda and gamma rays. So quite different. There's something weird going on in the center of Andromeda, and the kind of pushing out. This is the gamma rays coming from Andromeda's supermassive black hole. We have a similar thing in the Milky Way. This is not a selfie, but it's a map by studying the gamma rays from a satellite out here. We can see the kind of these two gamma ray bubbles sort of surrounding the Milky Way galaxy. So we can learn. We want to study these astronomical objects in any kind of light we can. Okay. Another way, just kind of as an aside, not really about telescopes, but one of the best ways to actually get better pictures of objects is to go see them. So we have the same instruments, the spectrographs, telescopes on spacecraft, and we fly around their orbits. Here's just kind of an interesting kind of a map of the solar system and where we've been so far. Unfortunately, as far as people go, we've only gone to the moon, but we've sent robots with instruments on them to all of the planets of the solar system. And the rest of this lecture, I'm not going to go through it here because you don't just look at it on the PDF. You can kind of see how the images have evolved over time. And how much better we are at actually getting images of these satellites of our planets. There's a little moon around Jupiter that we get. Now Hubble can see it too, but you can get a lot better when you go a space probe there. You can get a lot better reading. We actually have a space probe that this is actually from the Juno spacecraft that's orbiting Jupiter right now as we speak, taking scientific data. Okay, so that's it for this week. I'll interact with you through our discussion questions. If you have any questions, email me or put them on the help desk. And I will see you. I'll see you next week.